roommate, so we usually work together, and we were really confused on number. I don't know if it's okay for you to go over it yet because it's like not due,
Yeah.
but we did it. So it's question 13. So we did the 12 one. We're using the
Wait, now,
equation.
okay, now let's nail down which quiz you're talking about.
This is what is it called? Quiz 8.
Okay.
Yeah.
So hold on a second. Let's see if I can find that. Okay. Quiz 8. Okay. That's this. So that's due. This quiz is due.
I
Okay.
think it's due Sunday this week.
Okay. So is it class 8? No. Okay.
Yeah, it's class 8, quiz 8.
So it would be. I'm still. Can you see me? Can you see me struggling around here trying to find it?
This
Okay.
quiz,
So is this the week
week
4
4
class?
class 8. Yep, that one.
And you want the quiz? And that, let's see, is that
Yeah,
look
that
like?
looks right.
Okay. So let me see if I can get that up here and get my things, spotlight and stuff. And do you mind if I record this so the other rest of the students can see it? Or the
Oh yeah, that's okay.
Okay, thank you. Okay, so all right, so go ahead. I got it up here now.
So for number 12, we did it right. We got the 8,000 using the equation that you were showing us in class. But
This one, number 12. Okay.
Yeah, like the CL equals that,
Okay.
yeah, all that. But for 13, we tried to do it like substituting G's from 3.5 to 1 and then solving for V squared in the
Well, okay, now 13, you want the same conditions as up here. Same conditions, except it says level flight stall. So let's see, from the conditions for 12, what is the level flight stall airspeed? Okay. So now what did you do?
So what I have here is we have 2 on the left for the coefficient of lift equals 1 for, so we changed it. It's like, okay, let me try to write it out. Because I
Okay.
feel like just saying it's kind of confusing.
Okay.
That's what we set it up as. And for Q, and then we solve for Q. And then from Q, we solve for V squared.
Okay.
And then
and you got the 8,000 from the first problem, right?
Yeah.
Yeah. That looks right.
And then, but it was, I don't know, like what was going like wrong. Okay, so for Q, we solved it to be 6.66 ... just from that equation, what I just showed you. And then, so we set it to that equals 1/2.
How did you solve for Q?
From here, like through this equation here.
Oh, okay.
We solved for Q, which we got to be this.
Okay.
And then we set that equal to 1/2 rho.
What did you use for rho? What did you use for rho in there?
We have, it was 1.2 kilograms per meter cube, and then we tried to convert it to pounds per square foot.
No, the rho is the sea level density.
Oh, just sea level density.
Right? So it's right behind me, right here. I got my hand on it right there on the board. See it? Sea level density?
What hand?
Can you see me? I'm not sure what you're looking at. I'm looking at my own. Can you see behind me on the board here?
Yeah, I see your board.
0.0238 slugs per cubic foot. That's sea level density from my formulas that okay.
So do you just use that?
Well, you got to using the formula for Q, which is right above it up here, right? It's 1/2 sea level density times the equivalent velocity squared.
Yeah.
And you're at 1g, so the equivalent velocity is the stall speed.
Yeah.
At maximum C sub L. So yeah, so you put 0.0238 in there, and then the only unknown is v squared.
And then I square root that 23.6 is what I'm getting.
Well, you should get close to one of the answers.
Yeah.
That's shown in the problem.
Okay, let me write this out again.
So I'm going here on the back of, on my board behind me here. This board I've got behind me. I don't know if you can see it.
Yeah.
So we've got, let's see if I get this right. We got 3.5, and then we got 600, and we're solving for the weight, and that's divided by 1/2. Oh, and I give you the Q, right?
Yeah.
So the Q is what?
Gave us
23.5. So when you solve that, you get about 8,000 something, say 8,057 or something like that. I think is the actual answer I got. So we know the weight, right? All right. So now we know the weight. So for the second time, the NZ is 1. So the weight is 8,000.
Mm-hmm.
And you get 600. And then you're divided by 1/2 0.00238 times v squared, right? And that's the stall speed squared. And that equals 2. That equals 2. Okay, so, oh, I see. So this is what so we can bring the 2 up to the top here, right? And that would make this 16,000. Is that right?
Yeah.
If I bring the 2 up to the top, and then I'd get v squared to go over here. So I can move the v squared on the left-hand side and put the 2 down here from the CL max. See what I did? Okay, so if I do that, then that would make this 1,200. That's what I was doing before. 1,200, and that would get that would be. So I have 16,000 divided by 1,200 over 0.00238 is v squared. That kind of follow you? Follow me?
Yeah.
Okay, so let's see. So that's 16,000 divided by 1,200. 13 divided by 0.00238. Oops. 238. Okay, I get 5,602.
And then I square root that. Oh, okay. Now I get like 75.
And I get 74.8.
Yeah. Okay. Yeah.
So it looks like you had a mechanical problem with your fingers in the
probably,
right.
I think. Okay, let me just check.
Let's look at number 14. Now we've nailed that one.
Oh, at 14 I also got wrong.
Okay, so 14 is from the same conditions of 12. In other words, the weight, you figured out the weight and all that. What's the maneuvering speed? Okay, so now let me stop sharing and go back. Again, behind me up here, that's the 1g stall speed. We just figured this one out. We know everything in here. But now you're going to put the 3.5 in there. You see that? So your 2 equals 3.5. We know the weight, 8,000 pounds. You know the S, 600. You know rho sea level. So all you got to do is solve for maneuvering speed.
Okay.
And you see that if this is 3.5, then the square root of 3.5 times stall speed is going to be what maneuver speed is, because the square root of 3.5, when you put it inside NV, when you square that, the 3.5 is going to come out. It'll cancel this one. You'll have the same CL2.
Wait, could you say that again?
Okay, so what I'm saying is, if this number stays the same on 11, it stays at 2, right? It stays at 2. We did the 1G one, but now I added 3.5 to the numerator.
Yes.
Well, if this number stays the same, then the 3.5 has got to be added to the denominator too. Well, the 3.5 can only come from this v.
Yeah.
So the square root of 3.5 Yeah. So the square root of
Okay.
3.5 times the stall speed at 1g is going to be your maneuvering speed.
Okay. Oh, okay. Oh.
Yeah, that works.
Oh, yeah. Okay.
Yeah. Yeah.
Times the stall speed.
Yeah.
Okay.
So once you see it, then you can see how, if I could go to 9 Gs, if NZ was 9, if my airplane could pull 9, then to still have CL at 2, I'd have to have a 9 in the denominator. So I'd have to have 3 times the 1G stall speed. So if the stall speed was 76, then 3 times 76 in feet per second would be my maneuvering speed.
Okay.
Okay,
that
makes
works? Sense. Yeah.
Yeah, that's how you apply this formula to wherever the airplane is in the envelope. I think you got it nailed down now.
Okay.
And
okay, that was helpful. Okay.
Okay.
Yeah, those are the questions that we had for that quiz. Okay.
Nothing else? That's good?
Yeah, that's good.
Okay.
Okay, thank you.
You bet. You're welcome.
Okay,
You're
bye-bye.
welcome. Bye-bye. Okay. So I'm going to summarize this problem that we had in the last quiz 8, showing a video that's available. It's in one of my slides, but I'm going to finish this Zoom session since no one else is here right now, showing that particular video and nailing down how this equation works throughout the flight envelope. It's 6 minutes long, and let's see if I can get it running here. This is a flight envelope plot for a fighter aircraft using a Navy fighter, the F-18. And what it does, it's called a VN. The V stands for indicated velocity or equivalent velocity, and the N stands for G load, the number of G's that you can pull, or the load factor. So this is a VN plot, and there's your load factor. There's your load factor here, and here's your indicated airspeed across the A. And this is a plot at maximum angle of attack or maximum lift, which is C sub L equal to 2. So you can hold a maximum angle of attack anywhere on this plot shown by the red arrow, up to a maximum load factor of 7.5 Gs. You can't go any higher than that, or you will cause structural damage. So you can fly up here if you go fast enough, but you will break the airplane. And if you go too fast, then of course here's your structural damage over here. And then there's some negative G data here. We're not going to be concerned with that. I want to just explain what this curve means over here. So let's relate this back to what we've done in class. So here is the C sub L lift curve. It's C sub L is the same as this C sub L over here for 2. But we are going to plot the C sub L versus alpha curve, the angle of attack. And for high-speed flight, low C sub Ls. As you slow down, C sub L increases, angle of attack increases, and finally you'll hit the angle of attack limit. At the angle of attack limit, normally around 20 degrees, you'll hit a CL max of 2 for this aircraft, and the aircraft will stall. So this entire plot over here occurs at this point where C sub L equals 2 at the maximum angle of attack. Now here's the formula that we used in class, the C sub L formula right here. It's lift per unit area, or lifting pressure, divided by dynamic pressure, Q. Lift pressure over dynamic pressure. You can replace the lift with the number of G's times the weight. The number of G's times the weight is the same as the lift. So you end up with this formula. Now I see I have load factor. I can get velocity from Q because I know that the dynamic pressure, Q, is 1/2 density times true airspeed squared. So in other words, your dynamic pressure, 1/2 density times v squared, true airspeed squared. And in class we said that you could use sea level density if you wanted to relate this to ram pressure. So the dynamic pressure is 1/2 the sea level density times the equivalent velocity squared.
And this is what the pilot sees in the cockpit. He always sees ram pressure from the pitot 2, from the pitot system. So that's called equivalent velocity. And this equivalent velocity is what is plotted along here. So pilot reads this on his airspeed indicator. So at 1g flight, when nz is equal to 1, then the equivalent velocity will be your 1g stall speed, your level flight stall speed. And over here, I can see my 1g stall speed is going to be about a little less than 100 knots. Now I can go faster than that. If I go faster than 100 knots, then I will travel up this curve. And how is that done over here? Well, if I increase the velocity, I'll increase dynamic pressure Q. Let's suppose I double Q. If I double Q from what it was before, then the number 2 will come out here. If C sub L stays at a maximum of 2, if C sub L is going to stay there at 2, if I double Q, then I'm going to have to double NZ. So if NZ becomes 2, the Q out here, I'll still keep it max. So I can pull 2 Gs at twice the dynamic pressure. And to get twice the dynamic pressure, what kind of airspeed increase will that take? Well, to get a 2 outside the squared, I'll have to have a radical 2 in here. So radical 2 is 1.4. So if I had 100 knots over here, 1.4 would be 140 knots. So if I come to 140 knots, I come up here and I see, oh, I'll have 2 Gs. Do you see how that works? So if I doubled my 1G stall speed, that would put a 4 outside, and then I could have a 4Z. So if I doubled, so if I had 200 knots over here, if I doubled my 1G stall speed to 100 knots, come up here, and I'll get 4 Gs, 4 Gs. If I multiplied by 3, then the 3 inside the radical will become 9, so I could pull 9 Gs. So if I would be up here, if I double it to 300 knots, I'll be up here around 9 Gs, and that would overstress the airplane. So I can't do that because I hit maximum Gs at 7.5. So if NZ is 7.5, what airspeed would have to be in here? What multiple of my 1G stall speed would have to be in here to get 7.5? Well, you take the square root of 7.5, and that number, let's say it's, I don't know, 2.4 or 7, and 2.7 times the 1G stall speed, and you can read it off here. You can read it off here, and it's going to be right around well, 300 knots for this particular one. And that's how this works. This is called the VN diagram. It gives you the flight envelope. You can fly anywhere in here. If you're above maneuvering speed, which in our case is right around 300 knots. If you're above maneuvering speed, then or 280 knots. If you're above 280 knots, then you can structurally damage the airplane by pulling more than 7.5 Gs. If you're at 270 knots over here, then you cannot damage the airplane because the airplane will stall. It'll stall. That's it. Good luck.
Okay, so that gave it to you. And then one thing I didn't mention in that diagram was that at maneuvering speed, you can turn the tightest. You can turn the tightest most degrees per second, and that would be advantageous in any kind of air maneuvering. All right, so that's it. I don't see anyone else here. I'm going to sign off and make this video available to you. I will see you next week. I hope everybody has a good weekend.